up, guys. Today we're going to do a review on nuclear chemistry. Next time we'll do a review on electrochemistry, and then the next time is a test. So Thursday next week's a test. And the very last week of school we have an activity that you've got to be in class to get done, okay, for the whole week. So if you're not here, you don't get the points, and it goes down as a 0 because it is due by Friday. Yes? Okay, no questions. Okay, so what we're going to do is we're going to take some time and we're going to review. Come on. I love when they don't want to come up.
Got myself some rainbow goldfish. Nice.
Come on.
I swear the rainbow goldfish are like the extra salty. Yeah, they taste better. Yes.
Okay, we're going to look at the paper you picked up is actually going to be your notes for today. So we're going to go through them together. Okay. Hopefully we can get it to focus in now. Just thinking about it. All right, so first thing that we want to talk about in nuclear chemistry to review in our brain is what's the difference, well, first of all, what's the difference between radioactivity and radioactive decay?
Isn't decay safe? Wait, never mind. I take that back.
Radioactive.
Yeah.
Radioactive decay is the rate at which it goes away.
Okay, radioactive decay is the rate at which it goes away. What about radioactivity?
That's like a property.
It's a property. Explain. When something's unstable, so it does what? It gives off something, okay? Whatever, it gives off something. So radioactivity is when we change the nucleus. When an unstable nucleus releases something or is bombarded by something. Okay, so there are two sets of words that we need to worry about. First is going to be put on the reactant side of an equation. That is bombard or capture. So if it says bombard or capture, whatever I have goes on the reactant side. If it says release, emit, decay, those are on the product side. Okay? So why is it important that radioactive isotopes, I was going to say radioisotopes, used inside of us in the medical have to have relatively short half-lives? Why is that important? Good. So they go away before they do any more damage. So we're going to put it here. That's a good thing. Go away.
Yeah, me too. That'd be so useful.
What?
Growing an extra arm. If it was in a convenient place, that'd be very nice.
Okay, so now we're going to just do one of these problems, but you need to be able to do one or two or three of them. Remember when we were doing nuclear, we had two equations. We had the A equals AO to the 1/2 to the N power, or capital T, which is time, is equal to T1/2 times N. Those are the two equations that we used. AO. So amount after time, AO is amount of initial, 1/2, how many times I'm going to divide it in half, and N is the number of times I'm going to divide it in half. Total time is equal to the half-life times the number of times I'm going through that half-life. Okay, so let's look at what we have. In this problem, we have administered 20 milligrams of iodine. How much of the iodine is left after 40 days? So that's another thing we're looking at. And the half-life is 80 days. So this is total time here. This is T1/2. So using just those two, I can find N. Right? So that's what I'm going to do first. To find N, I'm going to take total time, which is 40, divided by 8. That will give me 5. Everybody okay with that?
Yep.
All right. So then I look back and say, oh, they gave me AO, the amount initial. So the amount initial was 20, so I can plug it in here. After time, I'm looking for the amount after time, so I'm going to take 20, and I'm going to divide it in half 5 times. Okay? So I can put it in as 0.5 to the 5th power times 20, and I can get an answer. I can take 20 and divide it by 2 5 times, whatever you want to do. So what are we going to get?
0.6. You want any?
625, right?
Yeah.
Okay, and that would be milligrams. So in that much time, I go down to 0.625 milligrams, which is really small. Okay? You need to be able to use both of these equations. You need to be able to find half-life. You need to be able to find the number of half-lives. You need to be able to find the amount initial or the amount that you have final. Okay, given the other things. So you'll be given enough in one equation to find something. Now, what if I'm looking for N, but all I'm given is A and O? Does anybody remember what do you do this equation?
Oh, if you're looking for N, you go to the T one. You use the T.
If all I'm given is A and AO, and I'm looking for N.
So then you just divide.
I have to do the log. Thank you. So that would be, I divide both sides, so I get log of A divided by AO. That's on one side. On the other side, I would have N log of 1/2. So that's what I'd have to do to find N. Okay? Find N. If you were just given A and AO, then you have to do log. Okay? That's the only time you have to do log. Other times, you're just using the regular equations.
Will that be on the test?
Probably. Okay? All right, so on the next part here, fusion reactions produce enormous amounts of energy. Why is fusion not used to generate electrical power? Say it louder. It's hard to contain. Just think about, contain, I can't spell. The nuclear bombs. That's not a tree, that's a bomb. Okay? So the mushroom cloud of a bomb. So trying to contain this would be really hard. Or trying to contain the energy of the sun in a room would be hard. Okay, that's the problem that we have with this, is it's hard to contain. So what is the purpose of wearing a film badge? If I'm a medical person and I have to wear a film badge, why do I have to wear a film badge? Yes?
So the radiation doesn't penetrate your skin.
Okay.
I was thinking of the things that people have when they work like nuclear power plants, like the little IPs that go like when they go home. It's like they have too much radiation.
There you go. That's what it's for. The film badge does not protect me. It just shows how much radiation I've been exposed to. So if I get exposed to too much, the film badge will change colors, and then my supervisor says, you are now released to go home, and you can't come back for 2 to 10 days because you've had too much radiation. No. So your job is to try and not get that to change because you want to work, right? So it's a twofold thing. It helps me know when I've been exposed to too much, and it helps my employer to know when I've been exposed to too much, and it saves me from being exposed to too much. Because I can look down and, oh, my badge is starting to change. Whatever I'm doing is wrong. It also helps people in the medical field when they're like doing x-rays and stuff to follow protocols. They don't stay in the room with you when they push the little button. They go behind the cement wall and the lead-filled glass to push the little button so they don't get exposed to the x-ray every time they take an x-ray. Okay, does that make sense? Okay, so you put what in your own words right here. We're going to use these. We're not always going to do beta decay here, but we're going to use these things to do other sorts of equations. As your assignments are coming in, I'm going to show you or tell you about the biggest mistakes that I'm seeing with your losing points here. So first thing, you're going to start with whatever they give you. Okay, so they gave me strontium 90. And then you're going to look at the word here. Remember, if it's decay, or if it's emit, or if it's produce, all of these go on the product side. If, on the other hand, it says bombard, or capture. Those go on the reactant side. Be really careful when you do your test and when you do your problems coming up to read the whole problem before you start writing it down, because it might say such and such was produced when, and if you put that as your reactant, you're going to have problems. So we're going to do a simple one here. We're going to do a beta decay. What is beta?
0, -1, B symbol.
Good. E or the V symbol. So you could use either one there. Please put a plus. Don't just smash the things together. That wasn't a big thing. You're getting this and what else? So remember the arrow's the equal sign. 90 equals 0 plus 90, right? 38 is equal to -1 plus 39. So 39 minus 1 is equal to 38. 39 on the periodic table is yttrium. Good. Okay, I want you to try and do the next one by yourself with a beta decay. Do not go on past that because we're going to switch it up. Do what I did up there.
Is it the same thing?
Same kind of thing, yep. I'm going to show you what the answer should have been here in just a second. See how good you are. Remember, each side of the arrow, top and bottom, have to equal each other. The arrow acts as an equal sign. Okay, I'll know you're done when you look up at me. Okay, I want a thumbs up, I got this right. Thumbs sideways, I didn't quite get this right. And thumbs down if I did not at all get it right. Yes, 2 thumbs up in the back. Okay, we're looking okay. If you were having problems with this one, remember, arrow's the equal sign. Top has to equal top on the other side. Bottom has to equal bottom on the other side. Bottom tells you what element. Bottom tells you what element. Okay, so I'm going to switch it up here. We are going to do an alpha decay now.
Oh, shoot. I already did.
I just told you to not do those.
So that would be 4.
Okay, so we're going to do 3755 cesium. What is alpha?
It's 4-2.
Good, 4,2. And what's the symbol?
Like lowercase a.
He.
Oh, it is.
Oh, it is? What?
It's either that or that. Okay, but you should know alpha is a helium molecule, and it has a positive charge. Plus, so 137 is equal to 4 plus what number?
133.
133. 55 is equal to 2 plus 53. 53 on the periodic table is iodine.
So,
Yep.
with beta, you minus it, but like.
Beta, you actually add it. Yeah, because we want it to.
You minus it.
Well, you're wanting these two to add to this, right? You're wanting these two to add to this. So a 7 minus 1 or 7 plus a minus 1 is 6, right? So 53 plus 2 is 55. Okay, I want you to do D as an alpha. Alpha decay on D. Do not do E. Wait.
I'm going to do gamma decay.
We're going to do a different thing.
Wait, and alpha's always heat.
Right. Okay, I'll know when you're done when you look up at me. We're going to do the same thing. Thumbs up, I got it right all the way. Thumbs sideways, I missed one thing. And thumbs down, I really screwed up. Okay? Just waiting for a few more eyeballs to look at me. You don't even know if you got it right yet. You got thumbs up. That's good. He's confident. Okay, here we go. How do we do? I want to see thumbs. I want to see thumbs. I see thumbs. Sideways. Sideways. What'd you mess up?
I put the wrong chemical symbol.
I get it more now.
Okay. We want to make sure we get this. These are easy points for the test, right? These are easy points. Okay, so on the bottom one here, we are going to do we're going to bombard it with an alpha particle. Okay, we're going to bombard it with an alpha particle.
So it'd be like the element.
Okay, tell me what to do. Tell me what to write. Okay, I'm going to have one person at a time, so give me one. Okay, it's on the reactant side, okay? Give me what, something.
5022 Ti.
52. Oops, that's one thing. Somebody else, yes.
Add the 4 2 helium.
4,2 helium, good. What else? Somebody else, give me something else to do. Yes.
Then there's the equal sign or the
Arrow. Okay, somebody else, give me something else to do. 54. Who said 54? What? 24. What's 54, 24? CR. And that's done. Yeah, but it's still 50 plus 4 is 54. 22 plus 2 is 24. Bottom number tells me what element. That's bombarding because I put it on the reactant side. Okay, so I can bombard with neutrons, with protons, with alpha, with beta particles. Okay, yes. We're not really subtracting, we're still adding because it's a negative.
Not the very top middle. Yeah. So you have to subtract.
We're still adding because a negative 1 plus 7 is 6, right?
She's on the like 8. The alpha. I know I saw it.
On which one? A, B, C, D? C. So this one. You're still going, 137 is equal to 4 plus this. So you're still adding, yes.
Oh, so like everything else we've done was like decay, emits, and produce.
Right. The top part was decay, emit, produce. The bottom part I did a bombard.
And so like if it doesn't like clarify, should we just like assume it's decay?
It will let you know.
Okay.
It will let you know. Okay, so last question on this side. What is the difference between nuclear reactions taking place in the sun and those taking place in a nuclear reactor? What type are they in each of them?
The sun is
Okay, so one person tell me, what's the sun? Somebody? Okay, what? It has hydrogen in it, but what type of reaction is going on there? I'm ignoring you two because you've answered a lot of questions. Sorry, not purposely, but you know what I mean. I want some others to answer. Okay, somebody else. I heard fission and fusion. Which one's which? Fission is what? The nuclear reactor or the sun?
Fusion is when you combine them and make the helium and you go up the periodic table, right?
Right.
The sun does.
Sun, good. This is fusion. So the other has to be fission. Remember, this one right here, we're having a hard time controlling. This is the bomb stuff. Okay? I can't control that. I have no control of containing that. But fission, I can control. I can contain. Okay? To contain it, I need to use moderators. Like in the nuclear reactor action, that's water. Moderates it, so it slows it down. Okay? All right, next slide. Write the nuclear equation when you're given it in words. So we're going to do the first one. Read the whole thing first. So it says radon-22 emits an alpha particle to form polonium-218. What do I start with?
222 radon.
Radon. 222 R, and is radon RA or RN? It's RN. Be careful. Radium and radon often get confused, and that's another one that a lot of you were messing up with. Okay, emits. So what do I put next?
Arrow.
Arrow. What is an alpha particle? 4,2 helium. Good. To form. What am I putting next?
Polonium.
What is polonium's symbol?
Yep. Same.
Yep. P, big P, little o. And what do I put in front of it?
218.
218 and 84, and I'm done. Okay? All right, I want you to try the next two on your own. Be careful on B. Be careful on B. Read it all the way through before you write anything down. Be careful on B. Read it all the way through before you write anything down. I see, said the blind man as he walked into the tree.
I can literally never find thorium.
Thorium's in the F. Very bottom row. Very bottom row on the left side of the F.
I'm dumb. It's been a little time.
Number 9.
They gave you the answer.
Okay, we almost done? Okay, I'm watching for eyes so that I know that you're done, and looking up here, we'll check one at a time because I want to see how well you did on each. Yeah, do both of them.
Both B and C?
Both B and C, yep. Want you doing both B and C. Want you to try it, make sure you can do it. Woohoo! Waiting for eyeballs so I know that you're done.
Oh, that's how you do it. You freeze it. And then you said C2?
Yep, then I can work it through and have it ready for you. Okay, here we go. First one. Let's see if you got it. Thumbs up, thumbs down, thumbs sideways. Here we go. Thumbs up, thumbs down, thumbs sideways. Show me. Did you get it? Did you get it? Did you get it? Oh, I saw thumbs down. Oh, no, 2 thumbs down. 3 thumbs down. Did you read the problem before you wrote it down? Okay, be careful because especially on these and on bombards, they might give you the product first. Those of you that did good job. Okay, let's look at C. I'm looking for thumbs again. Thumbs up, thumbs down, thumbs sideways. Did we get C? I want to see. Did we get C? I see thumbs up, but I see a lot of people not giving me an answer. Did we get it? Did we not get it? Okay, we got a few thumbs down, thumbs sideways. If you are thumbs down or thumbs sideways and you get to the assignment or you get to looking back at this, don't understand, please come in for a few minutes. That's all you're going to need, and we'll have it down. Or come up to the desk after. Let's go ahead and go forward here. Okay. Why are spent fuel rods removed from a reactor core? What does it mean to be spent? They do have plutonium, but it's still radioactive. What does it mean to be spent?
Went through a half-life.
Okay, what does... Okay, it went from uranium to plutonium, but it's still going to decay again. So what does it mean to be spent in a nuclear reactor? What is that nuclear reactor, that core, that reactor core? What are those fuel rods for? What are we trying to do with them? We're trying to what? We're trying to give off energy. So we need the heat to change the water from water to steam to turn the steam turbines to make electricity, right? If we don't have enough energy to warm that water to boiling, and maybe we only get to warm it to hot but not boiling, then the fuel rods are considered spent. Okay, so they don't have enough energy, and you're going to have to write your answers to these because I smashed a whole bunch in all different ways. Enough to boil water. Okay, so what do they contain? And you answered that, what? Mostly plutonium, but they do have some uranium still left in them. So they're looking at ways to reprocess the spent fuel rods to grab the uranium that's still there and pull it out. Okay, what happens to them once they are removed? Anybody know? Not immediately.
They go through a process.
To get the uranium out.
They're put in a cooling pond. It's just a pound of water outside of the site, and the water keeps the stuff under control. Okay, what does alpha particle do to the atomic mass of an unstable nucleus? What does an alpha particle, the decay of an alpha particle, do to the nucleus of an unstable atom? Yes? Yep, sorry. Okay, what does it do to the nucleus of an unstable atom? What is an alpha?
4-2 helium.
4-2 helium, so what does that represent? 2 protons and 2 neutrons. So it loses 2 protons and 2 neutrons. So how do we represent an alpha particle? 4-2 helium or alpha. Okay? And how do beta particles change an unstable nucleus?
They remove or they add one proton.
What is, let's go down here to 11. What is a representation of beta particle? 0, negative 1e, or beta, right? What's happening? What's that bottom number? What does that tell me? What do we usually use that bottom number to find? The proton is the change in the element. So I'm changing a proton to a neutron because the mass number doesn't change. I'm taking one and changing it. So I'm changing the element, but I'm not changing how many what's the total mass. Okay, so here we go down at the bottom here. How is a gamma ray different from an alpha and beta? Yes?
Doesn't have a charge.
No charge, okay. And anything else?
Its penetration power is higher.
Okay, penetration is a lot higher. Just put a couple arrows up. Anything else?
Isn't it? Oh, never mind.
It's a ray, not a particle.
It's a ray, not a particle, because it has no mass.
I wonder how I got that one.
I don't know. So how do we represent a gamma particle? That is a gamma particle. It also can be represented this way, but we often just represent it this way because there's no change. Okay? All right, down here at the bottom, I'm going to add a couple more because I want you to practice with doing equations from scratch. Here we go. You ready? Okay, we are going to start with 175 erbium. And I want you to do a neutron capture. A neutron capture.
Take it, wait, is ER
Neutron capture.
ER, what's the number?
It's down in the F. So neutron capture.
Okay, so when it captures something, it's under the reaction side. So you're gonna add a what particle?
Neutron. 0 what?
Wait, is it adding any?
175 the same thing, or 176 the same thing.
So if you did it correctly, what should you get?
176
176 CAR.
Okay, I'm going to give you another one. We'll do Einsteinium this time. Einsteinium undergoes alpha decay. Einsteinium undergoes alpha decay, and we'll do Einsteinium 260.
260.99.
Down in the F. Most of them are going to be down in the F or the lower P.
Wait, what is it doing?
Undergoes alpha decay. Alpha decay.
Wait, what's the...
Einsteinium's down in the F on the right-hand side of the F. Bottom of the chart.
369.
Almost the weekend. They got like 3 weeks left or so.
Okay, how'd we do?
Yes.
Okay, one last one. Okay, we're going to start with americium. 245. It undergoes an electron capture. Undergoes an electron capture.
What is it, 245? Electron capture?
Down in the F, americium. Undergoes electron capture. Electron capture. What is an electron capture? It's a beta particle. Yep.
Wait, so wait, say again what we're doing.
Electron capture.
Okay, so capture.
Electron capture. So add a beta. Adding a negative. Okay, so what I'd like you to do now is in your packet there is a review section for nuclear. It's assignment number 4. There are 2 half-lives that you need. They're on the board. Don't forget they're on the board. You can look them up on your phone if you need to, but they are on the board. Okay? Work on getting that done. The rest of the time is for you to work on that. If you finish before the end, come up and get a stamp so you get us an extra credit point. No, that is notes for you. That what we did right now was notes, just adding to your notes. So not the whole thing, just the assignment number 4. It will get to an electrochem review, and that will be due next the time after. So we'll do electrochem review next time.
Which assignment is it?
It is the nuclear review. It's a multiple choice like looking thing. It's the review assignment 4. Yep. It's a multiple choice like thing, review assignment 4. That's your notes.
Stuff for tomorrow.
What?
The stuff that we're doing on Tuesday.
Tuesday we're going to review electrochemistry. We're going to actually use that as notes, and I'm going to give you another paper for the assignment.
Is it this?
Yeah, it's a multiple choice one.